Today we're going to start looking at Unit 1, Concept 3, which is inverse functions or inverses of functions. So I want you to start on page 13 in your Unit 1 booklet. And pages 13 and 14 are your warm-up today. It might take you a little bit, so please pause the video, work on 13 and 14, and push play once you are finished. On page 13, explain how you can transform the function e equals 0.78d. So euros is worth 0.78 of each dollar, or 78 hundredths of a dollar, so that it will convert euros to dollars and help you figure out how much money you're spending in dollars, then write the new function. So in order to do that, to get d by itself, you want to divide both sides by 0.78. So to get d by itself, divide both sides by 0.78. So therefore, d is equal to e divided by 0.78. If we scroll down here, it's definitely a better deal in the United States, a quarter pounder with cheese is, because 5.95 euros is equal to $7.63, which is more than the $6.29 to buy the meal in the US. For this equation, to convert Fahrenheit and Celsius, how can we transform the function c equals 5/9 of the Fahrenheit minus 32, so that it will convert Celsius to Fahrenheit. So we multiply by 9/5 and then add 32. Essentially, if you think about it, in the first equation that we looked at, the original equation was given to us in multiplication. That was the only operation here, and we needed to use division to write the inverse. So in this equation, we have parentheses. Outside of the parentheses, we have multiplication, and inside the parentheses, we have subtraction. Well, we could technically, to get f by itself, we could technically say we're going to divide both sides by 5/9. But when you divide by a fraction, hopefully you remember that anytime you divide by a fraction, you need to multiply by the reciprocal. So you might have heard or remember your teacher saying, keep, change, flip. So if you had x divided by 3/4, you would do x times 4/3. Keep, change this, flip this. So instead of dividing by 5/9, we might as well just multiply by the reciprocal. So multiply both sides by 9/5. 5/9 times 9/5 is equal to 1, because technically it's 45/45 equals 1. And then we've kind of unlocked these parentheses. We don't need the parentheses anymore. The only thing left here is f minus 32. So we have 9/5 times c equals f minus 32. So the opposite of subtracting 32 is adding 32. So we've got 9/5 c plus 32 is equal to f. So that's the inverse. All right, so the answer to question 6, well, you probably want to pack shorts and t-shirts, since 25 degrees Celsius is 77 degrees Fahrenheit. Hopefully you wouldn't have just seen 25 degrees and packed a snowsuit. Number 7 and 8, basically both are opposite operations, so they're inverses of each other. And the key there is that inverses undo each other. Inverses undo each other. So when we write the inverse of a function, we're using it to tell us kind of the same information from a different perspective. So I might think about inverses undoing each other, like doing things that are opposites. So instead of putting on my shoes, taking off my shoes. So just things that undo each other. In math, we're talking about functions that undo each other. So we're going to investigate inverses a little bit more. From doing this activity in class, I do know that students tend to have a lot of questions, but you will be able to do this on your own. And then you can come back here and see how you did when you're done, or you could stay on here and I can kind of walk you through it. But you will definitely need 3 different colors for this activity. I'm going to get you started, and then you can hit pause. First, it's important that you follow the directions exactly the way they're stated. So we're going to fill in the table of values below for the given function. Here is your input for x and your output for y. So if we input -6, -4, -2, 0, and 2, we're going to fill in the outputs for the table. So you can go ahead and do that, and then plot the points on the graph. I don't think this step is difficult, so use one color to graph the function. And then we'll talk about using the 3 steps that you found from your homework to find the inverse of the function above. So hopefully you could get through steps 1, 2, and 3 on your own. You might get stuck on step 3. And then we're going to make sure you're careful with step 4. It says fill in the table of values for the inverse function. Tip for this right here. Tip for the best results, use the output values from the table above in your input column on the table below. So your output column from the table above, let me just zoom out, means the numbers that are here, the output values, you will use them as your input values in the table here. So you will not just use -6, -4, -2, 0, 2. You're going to use whatever answers you have here in this column. And then you'll have a new set of outputs. Then I want you to graph the inverse in a different color. State whether or not the inverse is also a function. Well, how do you tell if something is a function? You will do the vertical line test. Using a third color, draw the line of reflection of the 2 functions, or of the function and its inverse, and then write the equation of the line of reflection. Steps 7 and 8, you should have this information from your homework last night. So you are welcome to pause this and then just come back when you're done. And if you feel like you need some help, you can work through the parts with me that you need help with. Okay, so for the first part of this, for steps 1, 2, and 3, I graphed the original function in red. So the original function is in red on this graph. It's a linear function, and I did plot the points. Let me just move this out of the way for now. I did plot the points that I got from this table on the graph, and I connected them using a ruler. Use the 3 steps you found above to find the inverse of the function, or use the 3 steps you found to find the inverse of the function. So the 3 steps, in case you do not recall, 3 steps to find the inverse of a function. And sometimes I actually put that little one there. It should be f of x to the -1. So 3 steps to finding the inverse of f of x. The first step is pretty simple. We switch x and y. Then we get y by itself. So we solve for y, and then we replace y with f of x to the negative 1, or replace y equals with f of x to the negative 1 equals. So if you look at my work below, you'll see that I switched the letters x and y. So instead of y equals 2x plus 3, I have x equals 2y plus 3. Then I have to get y by itself. We start by subtracting this 3 to the other side, and then you'd have 2y. So to get the 2y, to get the y by itself, divide by the 2 on both sides. So how can you write your answer? 2 different ways. You could say that you have y equals x minus 3 all over 2, and then rewrite it as the inverse of x is equal to x minus 3 over 2. But since this is also going to be a linear function, I know that because x doesn't have an exponent, we could divide the 2 into both terms on the top. So if I divide the 2 into the x and the negative 3, this would be 1/2 x minus 3 over 2. So this is, I like this form because it's in the form y equals mx plus b, but you don't have to write it that way. If you put this in your calculator, the way you see it, you'll still get the same graph. Anyway, we really don't need a graph because if you continue down on the page and you simply replaced the answers from your output above into your input below, and you plug all of these values in to your inverse. So if I take negative 9, I do half of negative 9 is negative 4.5, and I subtract 3 halves, I will end up with negative 6. So if you wanted to do that, or using this equation, is probably is easier to use this equation. So if I want to plug in negative 9 minus 3 divided by 2, and then you have negative 9 minus 3 is negative 12 over 2 equals negative 6. So there's your negative 6. After you finish that, you would plot all of the points in this table right here, all of these coordinates, negative 9, negative 6, negative 5, negative 4, negative 1, negative 2, and continue to plot the points, and you'll end up with the blue line, which is the inverse of x. What you should have learned last night is that, oh boy, that's really zoomed out. If we graph the inverse in a different color, is the inverse also a function? So the original is a function, so the red line is a function. The red definitely passes the vertical line test, and the blue also passes the vertical line test. So the answer to that question is yes, it's also a function. And then the reflection. The line of reflection is the line y equals x. I put that in there as a green dotted line to show the line of reflection, and that is the same line of reflection for every single function and its inverse. So a function and its inverse always have to reflect over the line y equals x. So is the inverse also a function? The answer is yes. We knew that because it passes the vertical line test. Write the equation of the line of reflection. This is the same for every single equation and its inverse. The equation of that line is the line y equals x. Just so you know, in the form y equals mx plus b, that's 1x plus 0. So m is equal to 1, but this line has a slope of 1 and a y-intercept of 0. So again, if we go back up and take a look at it, we see that this green line that's dotted has a y-intercept at 0 with a slope of 1, up 1, right 1, up 1, right 1, up 1, right 1. So that's also just FYI, that is the parent function for all linear functions. Okay, what did I just do? Here we go. For all linear functions. So if we go to the next page, you are basically doing the exact same thing, but this time you are looking at a quadratic function and its inverse. So same steps. You fill in the table of values here. You use the output values in the other table as your input. You're going to use the 3 steps to find the inverse of the function above. So put those values in here. And then graph the inverse in a different color. Is the inverse also a function? Write the line of reflection or draw the line of reflection and then write the equation. And then we'll talk about the analysis. So what you basically should have when you finish is you should see a parabola in red. When you got down to here, you may have, and it's really important, you may have had your function written as y equals the square root of x minus 2 minus 3. So while I do show my steps here, switch the x and the y, the first thing we need to move is subtract the 2 to the other side. Now you would have this power of 2 that you have to get rid of. So in order to get rid of squared, you take the square root. And when you do that, this is super important right here. When you take the square root of both sides of the equation, you need to put a plus minus in front of the square root. Now you may have forgotten that because it could have been a while since you've done this, but it's important that it's there. So if you had y equals the square root of x minus 2 and then a minus 3 outside, or you could have had a negative 3 out front and then you just had plus the square root of x minus 2. Either way, I'd prefer it's written this way though. Then you need to add in the fact that this is got to have a plus or a minus in front. So I talked about the parent function of a linear function is this line of reflection. So the other thing you need to know is that once we have a square root in our equation, it is considered a square root function. And the standard form, like I kind of talked about for a linear function, we write it in the form y equals mx plus b. Well, we could write, if we look at the function we were given here, the original, that is a quadratic. I know that because it says x squared. Well, the standard form for a quadratic, the standard form is ax squared plus bx plus c, which is good, but the one that we have written there is f of x equals, and we have it written in what's called vertex form, a times x minus h squared plus k. If you don't remember learning about that, we'll talk a lot more about this as the semester goes on, but we like this format better than standard form because it just gives us more information. So if you have a square root function, it's written in the form a radical x minus h plus k. So this is just kind of the proper way to write things. All right, so my inverse is written as plus or minus square root of x minus 2 minus 3. And if you look at the table and you weren't sure how we got some of those values, just keep in mind that I told you to take your output column and rewrite it in your input column. Well, if you went through and plugged in the number 6, you should have seen, and you can redo it now if you didn't have the plus and minus, because then if you didn't have the plus or minus, you would have just done 2 minus 3 and gotten -1. But now you have to also consider the fact that you could be finding the negative square root. So we split the problem and we use the -2 as well. So -2 minus 3 equals -5. So you should get 2 different answers when you plug in 6. -1 and -5. Same would happen with 3, and with 2, that would not happen. Okay, so that means, what if I want to graph this on the calculator and I take a look at it on the calculator? I type in my 2 functions, or my function that's up here, and my inverse, which I'm not yet sure if it's a function. So you go to y equals, and you type all this stuff in. You type it in, and you take a look at it, and you see that. And hopefully you think it looks a little weird. Because it looks a little bit off, the reason for that, if you think about it, is we're supposed to have a line of reflection at y equals x. So if I go in and I just type in the line y equals x, there it is. If I hit zoom square, it will make my graph look a little nicer. Right now it's in zoom standard. So if you hit zoom 5, it will make it so the intervals here look the same here on the x and y axis. And still, if that's supposed to be a line of reflection, if something's reflecting over this line, it should look the same as it did before, right? A reflection over that line shouldn't look different. So if we had a line of reflection like this, that's hard to see, sorry. If we have a line of reflection like this, if that's a mirror, if I'm kind of, I guess I'll make myself happy. If I'm happy, here's my hair, and this is the line of reflection, well, I wouldn't just see, if this were my hair, I wouldn't just see half my hair, right, when I reflect it. Okay, my face is a lot bigger in that one, but I would see all of my hair, right? So I'd have to have hair this way too. So y is this part of my graph, looks like it's reflecting over here. But the left side of my graph is missing. Why is there no reflection? Okay, so if you graph it on a graphing calculator, I want to point out to you that you have the positive square root here. You'd have to separately put in the negative square root because you don't have a button on your calculator that says plus minus. So to see the rest of the graph on the calculator, you would have to enter it separately as the negative square root of x minus 2, then hit your right arrow to get out of the radical and enter -3. If you do that, we'll then see the second half of that graph. So we should absolutely have -4, and I'm just getting these so they're accurate, 6, -5. So here's the other half of that graph, and now it's a reflection. Imagine folding your paper on this dotted line, that this parabola would overlap with this parabola. and to point out that that orange left side would kind of lay on top of the bottom half of that parabola. Okay, so a couple of things I want you to notice about that parabola is that that sideways parabola, first of all, here's our vertical line test. If we take a look at the original function, the quadratic, this passes the vertical line test. But when we get over to this side, this does not pass the vertical line test. So this is the inverse of that function, but it's not a function. So this is a function, but this one here is not a function. And it's important that you can see that. If something's not a function, it's called a relation. So is the inverse also a function? The answer here is no. Okay. Another important thing that I want to point out to you is that you remember when I graphed this on the calculator and when we only entered the positive square root, we saw the top half of this. The bottom half of this came from entering the negative square root. So that'll come into play a little later in our lesson, that the bottom half of this sideways parabola is the negative half. Well, if you look at the reflection, that must mean that for our quadratic function, that the right side would be the positive side and the left side would be the negative side. So again, that's something that'll come into play a little bit later. Okay, so for our analysis, if you skipped through some of this, hopefully you'll catch up and just listen to the analysis. We want to find the domain and range of the original function, and we want to find the domain and range of the inverse. What do you notice? And then how can we restrict the range of the inverse so that it is a function? Okay, so over here I have written down the domain and range of the original red function. And the domain and range of the inverse. Another thing I want to point out is that, remember the first step of finding an inverse is to switch x and y. So I'm just taking a look right now at the vertex here is negative 3, 2. The vertex of this sideways parabola is 2, negative 3. Notice how the x and the y switched. So that is true for every point on the graph. So this is negative 1, 6, and this is 6, negative 1. So the other question that we were asked down here is, what do you notice? The domain and the range switch. Think about it. The domain, if you don't remember what the domain is the set of all x's of a function. The range is the set of all y's. So in this function, the domain is negative infinity because it's going left forever and right forever. But the range is restricted. The lowest point on this graph is 2, the lowest y value. So domain is the x's, range is a list of all the possible y values, and the lowest possible y value here is 2, but then the graph goes up forever. We use a bracket to show that 2 is the lowest number. If you look over here, the domain, how far left and right will the blue graph go? Well, the furthest left is 2. So we've got the 2, and then it goes right forever to infinity. The range is how far down and up will it go? How far on the y-axis? Well, it can go down forever and up forever, so negative infinity to infinity. And hopefully you notice that all of the x's here became all of the y's here. All of the y's here became all of the x's here. So the domain and range switch. And the last thing I asked is, how can we restrict the range of the inverse so that it's a function? Well, remember I said that this bottom part was the negative part of the function, and it matches up with the negative part of the parabola. If I want this to be a function, I want it to pass the vertical line test. Well, all I really have to do is say, hey, before I graphed this negative part, this did pass the vertical line test. So if I get rid of that and I look at the graph, that now, right here, this is now a function. So essentially, you're allowed to just say, I want to restrict this and make it a function. You'd only be asked to do this some of the time. It's kind of an extension of a question on this topic, is if this is not a function, how can we make it a function? And my advice to you is to always erase half of the parabola. You could erase the bottom half, or you could erase the top half. But it is better to just get rid of the bottom half. Get rid of the negative part. It's going to make your work easier. If you restrict the range here, think about it. If you restrict this range and you don't make it go negative infinity to infinity, now what is the new range? So if we restrict the range, if we restrict the range, how low does this graph go now? Well, now this is the lowest point, and it has a y value of -3. So my restricted range would be -3 to infinity. And what would that do to my original? Well, remember, the range here would become the domain here. So if you restrict the range on this graph, you would have to restrict the domain on this graph, which would mean we would erase this half as well so that there's still a reflection. That would mean that the domain here would be -3 to infinity, right? How far left does this go? The furthest point left, the x value is -3. Okay, so for the range, we use the y value, and for the domain, we use the x value. Okay, that's a lot of information in this investigation. So I didn't write down an answer here. How do we restrict the domain, restrict the range of the inverse relation so that it is a function? You could write, get rid of the bottom half of the sideways parabola. That would be fine for now. So while we're on this page, I have this graph drawn on the right side of my screen. I just wanted to point out that in this particular investigation, we had a parabola opening upward, and we saw that when it reflected over the line of reflection, the parabola then opened to the right. Well, a typical question for students to ask is, what if we start out with a parabola that opens downward? So instead of a parabola that opens upward, what if it is opening downward? Well, then if it reflects over the line of reflection, you would have a sideways facing parabola that opens to the left. So this is true all the time. This is something great for you to study and know. that the reflection over the line y equals x of a downward facing parabola would open to the left. The reflection over y equals x for an upward facing parabola would open to the right. All right. Lots of information in there, but I wanted to go to this page and talk about what a one-to-one function is. So how do we tell if a function is one-to-one? So we're on page 17 in your packet, and you have a lot of room here to write stuff. I'm going to put up my notes and just kind of talk you through it. You are welcome to pause this. I think a good thing for note taking is that you can pause this now, write it down, and then listen, or you can listen first with your pencil down and then pause this when you're done, when you're done listening, and then write it down so that you're not writing and listening at the same exact time. Okay, so in the first graph on this page, we're looking at a linear function. And the second part of the page, you're looking at a quadratic function. So we basically are splitting the page and comparing the two. So if we just focus on the linear side, you've got two lines reflected over the line y equals x, and the graph looks something like this. Is f of x a function? So f of x is what I have shown up here in red. Yes, that's a function. Is f of x, the -1, a function? Yes. If you answer yes to both, then the functions are called one-to-one. So what is the definition of one-to-one? Well, it means that they are inverses of each other and they are both functions. Well, if that's the case, a one-to-one function means the original, or one-to-one means the original is a function and the inverse is a function. And that ultimately means that they both pass the vertical line test. And then I wrote under that, and they'll pass the horizontal line test. Well, what do you think the horizontal line test would be? Well, here's a horizontal line. If I run this on the red function, it only touches once. So that basically means that if I turn this and make it a vertical line, that the blue function, the blue will only touch once as well. Think about this. What is the inverse of a vertical line? And your answer should be a horizontal line, right? So that would be the reflection over the line y equals x. So if the red passes a horizontal line test, it ultimately means that the blue will pass the vertical line test. So the horizontal line test is a shortcut to knowing whether or not the inverse will pass the vertical line test. And it works because a horizontal line is the inverse of a vertical line. All right, so if we look at the quadratic, the original function is in red and the inverse is in blue. Is the original a function? Yes. Is the inverse a function? No. We know that the inverse is not a function. We just looked at this on our investigation, but we know that, oh boy, we know that it will fail the vertical line test. So here we go, vertical line test. We make that more vertical. Touches in two spots on this blue sideways parabola. Okay. Well, I have written down shortcut. If the horizontal line test fails on the original, then it's not one-to-one. Okay, so let's turn this sideways, and we can see that if I have the original function and it fails the horizontal line test. The horizontal line test touches twice. So on the original function f of x, the vertical line test works, it's a function, but the horizontal line test fails. That means that the inverse will not be a function. So notice the inverse passes the horizontal line test. So it only works on the original because the inverse of a horizontal line is a vertical line. So it means the inverse will fail the vertical line test. Restricting. Restricting means that if a pair of equations, one being a function, if it's not one-to-one, then they're not both functions. So one of them is a function and one is not. Restricting is the way that we can make this one-to-one. So if I say, okay, well, this isn't one-to-one, how can we make it one-to-one? How can we restrict the domain of one of these or restrict the range of one of these and make it one-to-one? All that means is you're going to get rid of half of the parabola. So I'm going to move my vertical line test out of the way, or let's take a look at this from the perspective of the horizontal line test. If I'm just put this on the side for a second, if I say, okay, I want to make this pass the horizontal line test, the original function, the red one, I want to make it pass the horizontal line test. So I'm going to erase half the parabola. Again, I suggest you always erase the negative side or the left side. And then if I get rid of the left side here, I'd be getting rid of the bottom here. And now, let me zoom in. Now, if I use my horizontal line test on the red, it only touches in one place. And that means that it is one-to-one. I can double check and use my vertical line and make sure that it only touches the blue in one spot. Let me fix this up a little bit. Okay, I'd say the trick in doing this is the easiest way is to keep the vertex and the right side. And then you'd have the reflection of your vertex and the top. So the vertex is the key. I think here it looks like it's the point -2, 0. And on the right one, on the inverse, it's the point 0, -2. So that's a good way to check to see if things are inverses. Pick a point and make sure that the inverse of that point is there by switching x and y. Would this have been possible to restrict if I went all the way up to here? What if I erased all of that? Could I do that? Could I change the domain to start? How about we even make it start here? What if I change the domain of this one so that it starts at the point 0, 4? So now I've changed this, so the domain, the furthest left that this will go is from 0, and then it goes to the right forever. The range here would be the lowest point here, looks like 4. This is a 5. I guess you can't see that on your screen. So 1, 2, 3, 4, 5. So 4 to infinity. That would change my restriction down here. So that means I would have to start at the same point. So if this is 0, 4, then I would have to start at the point 1, 2, 3, 4, 0. So you don't always have to start at the vertex when you're restricting, but it makes the most sense to. Most people just go to the vertex, but you could start somewhere else. So now, if I look at the inverse, the domain is how far left and right. So the furthest point to the left is 4. and then it goes to the right forever. For the range, the lowest point going low to high is 0, and then it goes up forever. So again, notice the domain and range switched. So here for the domain, we use the X value. Here for the range, or for the domain, for the range, we use the Y value. Okay. I'm going to put this up on the screen one more time in case you do want to copy any of that. When you're done, you can pause this and you can then hit play. Okay, the last thing that we're going to do is, you could skip the top of that page. We just answered those questions. So here are the steps to writing an inverse function. They're the same as what I wrote before, except at the top I wrote replace f of x equals with y equals. So what I would like you to do is to work through all 4 of these problems. You're going to follow the directions for each function below, find the inverse, then state whether the inverse relation is also a function, and then answer the question, is the original function 1 to 1?